So today is September 13th, and welcome to fall, everybody. I'm enjoying the weather here these days. Let's just see here. What are we looking at? This is is this a view of the PowerPoint from the Drive application, or is it? It's not a PowerPoint presentation, is it?
No, it's
okay. It's whatever it is. Yeah. So let's just remind us what we're doing here. You know, in the spring we talked about sort of the nuts and bolts. So basically, you know, what's the purpose of this as well? I mean, the purpose is for us to try and understand how we can interpret just the radiation. If you look at the sources of information we have in the universe, even things like dark energy and dark matter, we know about their existence because of spectroscopy. Isn't that amazing? I mean, it's sort of totally counterproductive, but we don't know of dark matter from any other source, like gravitational waves, neutrinos, cosmic rays. We know about them because of spectroscopy, and we know about it because we have things called the Doppler effect in an Einstein's universe, which just basically stretches and shrinks the time scale upon which things go. And also we know about things like gravitational redshift and what have you, as well as special relativity. So we're able to probe the universe because we have things like Doppler shifts. How can we measure a Doppler shift? I'm going right back to basics here. Well, the Doppler shift is, you know, if we have a pure tone in our police car going past, then you can hear it going, yeah. So you have a periodicity in the sound that's changing. But in order to do that, you have to have a relatively pure tone. If you have the wheels of a car going with white noise, you can't tell. You can't tell it's coming towards you or further away from you. You have to have a pure spectrum. And it just so happens that the constants in the universe, things like the fine structure constant, electron charge, the mass of the electron, all these sort of ingredients of a standard model turn out to produce narrow spectral lines, just like a police car that has a one tone, but it's nature that's provided us with that. And so this is all tied together with things like the whole business of chemistry. So the fact, if you go all the way, push hard in terms of philosophy and say, why are we able to measure the universe the way that it is? It's kind of related to us being part of chemistry as well, because chemistry and spectroscopy are entirely related. Both are sort of essentially about the dynamics of electrons moving around in atoms. That's what they are. DNA is that. So a universe that is capable of making us is also a universe that's capable of making narrow enough spectral lines so that we can see galaxies moving further and further, that are faster and faster as they get further and further away. If that weren't the case, we wouldn't be here, and neither would we have the Doppler effect. So it's not a very good argument about anything really, except just an observation. All right. So what did we talk about? We talked about a bunch of things like the classical plasma physics. So there's no quantum mechanics in plasmas. I mean, you just have these very short wavelength de Broglie waves that look like straight line trajectories, and they hit ions and they hit particles and they sit inside a stellar atmosphere. Everything we see in the universe is really bright enough. Otherwise, by definition, we don't see it. So unless we see through something, and then we see like an Einstein cross image, or the interstellar medium taking a nick out of something bright, but that we need something bright there to see it in the first place. And in order to do that, that means there has to be a lot of energy per unit, per particle in the plasma. What's energy per particle? If it's relaxed, it's temperature. That's all it is. So you have to have a high temperature to see anything really at all. And if you have a high temperature plasma, you have to have something sustaining that. And the way that works is gravity pulls the galaxies and the universe together, and then you have more gravity pulling in the mass into little things like stars and quasars and black holes and stuff. And then you have this stuff around the stars that's all lit up and bright. because it's an imperfect process. I mean, things bash into each other. You convert conserving angular momentum in this direction. You have a lot of angular momentum in that direction of an accreting star. You have to get rid of this stuff, and the process of getting rid of that conserves the angular momentum in a fashion of the entire cloud such that it warms up and radiates. So it's a kind of coupling between a battle between gravity and inexorable pull, and then the evolution of the universe towards providing what looks like a lower entropy state with all this stuff plumped into stars and galaxies. But actually, of course, second law of thermodynamics, the laws of big numbers of things, say even though we've got reversible processes going on in Newtonian mechanics, on average, this thing is going to get hotter and increase the entropy, and that's what we see, and that's what we're trying to understand. All right, so that's really the big picture. Now, the purpose of this HAO, and for people maybe that eventually look at these things, is to talk about an example of the sun, basically, as an example of one of these things. It's undergone all those things I just talked about. It's also undergoing the business of not being able to get rid of magnetism. Magnetism is really hard to get rid of. Electricity is really easy. All you do is you move charges around and you can get rid of electric fields. Sometimes the sun insists on not getting rid of an electric field, and then it's got a quandary. It's got to find a way out of this system having a very strong electrical force. And those things can happen only if you have a strong EMF generated, say during evolution of a flare. And then, but that's a very quick thing. So on average, there's no electric field in a plasma, so we don't have to worry about those too much. There's a few things like electrons whizzing past atoms and stuff like this. But ultimately, a thing like the sun is obliged to make something called the corona, which people here know about better than I do, from helicopters and other places, and with instruments, and what you have that they've been involved with. And the corona is simply a result of the untidiness of the magnetic field in the sun, because deep down the magnetic field has to do what the sun says. High up, the sun has to do what the magnetic field says, because the forces are so much stronger further away, and in magnetism, whereas the plasma drops off exponentially. And the corona just exists because the sun's trying to get rid of all this, sort of churning and burping up of magnetic fields, and then it's twisted and it's turned into these things. And the exact process of going from what we can observe on the scales of multi-megameters down to the dissipation, irreversible dissipation scales, is incomplete. We don't see the whole thing. But basically, the corona exists because it has to. I mean, there's a small 0.1% of the energy of the sun that always is associated with magnetism. That magnetism floats to the surface, it gets tangled, it gets pushed around, and finally, when it gets out far above this thing called the chromosphere, the density dropped off so much, like the ionosphere of the Earth, the thing becomes simple again. I mean, if you look at the magnetic field of the Earth, it's quite complicated at the Earth's surface. I mean, your compasses point in different directions depending on where you are in latitude and longitude, and it varies with time. But if you look at the magnetosphere, it's this beautiful, teardrop-shaped thing, except if one of these nasty things that people like these guys observe all the time comes through and disrupts this thing, and then all hell breaks loose. And then all this nice teardrop thing has to sort of think, holy shit, I'm suddenly out of balance now because the magnetic forces have changed, the tensions and the pressures have changed. I got to do something. And then we get these things like the Northern Lights. All right, so that's basically the idea behind all this, is to say, well, how do we really know all this? In the magnetosphere, since when was the first journey out of, it was the Luna 1 and Luna 2 discovery of the solar wind after Parker's 1958 paper. So it's like 1960 when the Russians got their spacecraft out of this thing called the magnetosphere, which we sort of knew must exist. I mean, if you look at Dunge's theory of reconnection in the Earth, it was driven by the notion that there had to be opposite polarity fields in the tail of the magnetosphere. But that was before it was even observed. But of course, we knew about that because we had a potential field model and we knew about the solar wind. So it sort of had to do this. But it wasn't until 1960 that this spacecraft flew through the magnetosphere and into the area of non-protection of the solar wind, where they suddenly started measuring this flux of particles. And that was then vindication of Chandrasekhar's decision to publish Parker's paper in spite of being rejected by the referees in 1958. But we know about the magnetosphere stuff now, largely from spacecraft that we've flown through, but that only started in the late 50s, right? And with people like at NRL, Richard Towsey, getting hold of these V2 rockets that were otherwise landing on London and places. Much better to make them land in New Mexico, I mean, that's the much better plan, or wherever you're shooting them from. And, they were measuring this stuff from then on in, but really, aside from our local part of the solar system, all the way out to, sort of the Oort cloud or something, the Voyagers are out beyond the heliopause, so the place where the interstellar medium doesn't know about the sun at this point. All it knows about is a few photons coming from that direction versus the rest of the universe. I mean, you're closer to the sun than you are anywhere else. Apart from that, the plasma looks the same everywhere, pretty much. So how do we really know about this? Well, it's because of spectroscopy. I mean, and like I said at the beginning, the business that even the dark matter, even the dark energy, is something we know about because of the presence of non-dark photons reaching us and nothing else. So this is really critical. Okay, so where do we get to all the way through this last spring? We got to the point where I was talking about two kinds of things. One is a bath of energy in the plasmas that we see. We know that we need a plasma to radiate, and for it to be hot and to see anything at all, we better have some photons coming towards us. But associated with that, my picture of what's going on is you have this plasma. It can be a very dense plasma, like the core of a neutron star or something. And it's still not, that's actually not a plasma, I suppose, but the core of a white dwarf, a degenerate plasma, a core of the sun, which is a very, very hot, dense plasma in the middle. And you better have and also, as you come further out for these gravitationally collapsed objects, all this internal energy is built up owing to the gravitational pull and then the ignition due to fusion of stars on the main sequence. And we have all these Coronian things. So what I think about in a plasma is we have a bath of energy contained in the plasma itself. So this would be NKT for the pressure, 3 halves NKT for the internal energy, multiplied by the volume of the star. That's a huge amount of energy. And then you have half rho v squared, which is the local kinetic energy. But then you have things like internal degrees of freedom of the atoms. So we have the energy associated with ionizing a hydrogen atom. If you've got a plasma, that's pretty much what's going on. And that amount of energy is a lot. That takes a real effort to pull that thing out. So we have a bath of energy associated with motions. That's just classical mechanics. And then we have a bath of energy embedded in there in terms of internal degrees of freedoms of the atoms. So if, like on the Earth, we breathe the air we breathe, and there are very few, thankfully, very few ions. We're not breathing oxygen plus, right? I mean, that wouldn't be very good. And the reason is there isn't enough energy here to ionize it, but there is on the sun, because you've got this huge flux of radiation coming through, and the sun, in sorting itself out, trying to get rid of this energy slowly, creates these very hot plasmas from which the radiation escapes. So we've got the plasmas containing internal energy and macroscopic energy of flows, but we've also got magnetic energy in some plasmas. It's very small in the solar interior, dominating in the atmosphere above. So we got these reservoirs of energy here, but then we've also got a reservoir of electromagnetic energy in the way of photons. Now you think to yourself, okay, what's the difference between magnetism and electromagnetism? I mean, aren't they all part of the same thing? Yes, they are. But what's going on here is that the magnetic fields that we see associated with the sun and we measure in around something like the sun are all to do with the presence of steady electric currents with no acceleration of charges per se. I mean, there are microscopic accelerations as these things hit the plasma, but you have steady electric currents, steady on a speed of light time scale. So, you know, the light crossing time for speed of light across the radius of the sun is about a couple of seconds, right? I mean, it takes a couple of seconds. So if we have stuff going on and we can see it like a prominence lasting for a week, we know for sure that it's associated with magnetic fields, and those are very steady things on a large scale. And a steady thing will produce things like dipoles, quadrupoles. If I were to say, let's put a steady current here and try and compute in the space around it what the electromagnetic field looks like, there would be no net accelerations that I would need to worry about, because these things would sort of cancel out in random thermal motions. That's not true what I just said, so we'll get there in a minute though. But if it's just steady, then the magnetic fields drop off as like 1 over r cubed for a dipole, 1 over r to the 5th for a quadrupole, 1 over r to the 7th for octupole. So basically what I'm saying is these are localized. And at infinity, the magnetic field of our sun doesn't affect the magnetic field of Alpha Centauri, right? I mean, that's one of the closest stars we have, right? On the other hand, if we do have little bits of accelerations of charges, we know from Maxwell's theory. So now I'm relaxing the idea that you've got a steady current or a steady amount of electrical energy that's causing these magnetic fields steady. Remember, according to the speed of light travel time. Now, what we do is we allow the fact that the same theory, Maxwell's theory, but we allow for the notion that there's a finite travel time that it takes for a signal in a steady magnetic field to make it to a certain place. But if it's steady, we've got no changes. So we've got d2 by dt squared of any charges in here is 0. That means there's no radiation. If you look at Maxwell's equations and you look at the mechanisms by which you get steady electric and other magnetic fields, and then you get moving, accelerating particles. So I just look at one accelerating particle. This is the classical Thomson calculation, scattered light off the corona, right? And what's going on there is you've got an accelerated particle, it's oscillating. Right, that means it's accelerating. You know, d by dt of the x equals minus m omega naught squared x. So you've got e to the I omega t. So you know what, you can differentiate it, and you know that the acceleration is omega naught squared x for the displacement. So when x is 0, you've got no acceleration. It's at the core, at the center. When you're out at the extreme variation of this classical dipole, it's turning around. So you've got a very strong second derivative. And we know that when we include that term and put in the retarded time into our equations for the generation of magnetic field, using the same equations as Maxwell with the smooth one, but this little bit of acceleration causes the radiation to have a little nick sideways, sorry, the magnetic field to have or the electric field to have a little nick sideways in it, such that the radiation from a point here, sorry, the magnetic field vector from a point here is going to say point in that direction. And then as it's moved here, in the time that you've spent waiting for that thing to get there, then the charge is moved from, if I draw an arrow to the charge there, and now we draw an arrow to the charge here, the magnetic field should be there, but then now it's moved over here. So the magnetic field vector has gone in that direction. So the local magnetic field has gone from there to there. That means there's been a transverse component added to the electromagnetic field. That's the radiation component. And so unlike Alpha Centauri not feeling our steady magnetic fields, when we have an accelerating charge, Alpha Centauri, if you had a good coronagraph, you could observe the same corona that you guys measure, on the sun as we do here. And that's because then the magnetic fields on the Earth, on the sun, drop off, and the steady magnetic fields drop off in Maxwell's equations according to 1 over r to the n greater than 2. But the radiation drops off as 1 over r squared in terms of the intensity. The electric fields and the magnetic fields drop off as 1 over r. So it's this long distance thing that separates Maxwell's equations for steady things versus accelerating. And so finally, I've got to the end of my first page here, which is to introduce the notion that radiation is a thing that traverses the whole universe, and that we can all detect. People on Alpha Centauri can look at our corona, we can look at their corona, etc., etc. So what did we put together so far? We know that, let's just dive straight in. We looked at stationary and dilute plasmas. Now I'm going to talk about a different kind of time dependence. So now I'm looking very specifically at these actually fitted on a PowerPoint slide. So if you wanted to bring up the PowerPoint slide, you could read what's underneath those things. So now I'm looking at the atoms and ions embedded in a plasma in some remote place, the sun, you know, Markarian galaxy, whatever the hell it is. And I look at, and we know that one of the most useful things for us is to look at energy levels in the internal degrees of freedom of an atom. If we look at, say, bare nuclei, like a proton and electron, we can have radiation associated with the acceleration of the electron. Remember, I was talking about acceleration. As it orbits the proton, maybe it's captured, and then it goes from a free state, which looks classical, to a bound state, which is very much a small quantum state that doesn't decay. That could lead to continuum radiation. But remember, we were mostly interested in the line radiation because it produces very narrow features which we can use to track the motions of plasmas. In fact, if you look at solar physics, essentially all the information we know about the corona is due to the fact that the plasma is glued to the magnetic field because the ions can't get far from the individual field lines. And also we can measure the Doppler shifts of these things, and we can measure the proper motion. So we get a three-dimensional picture of the velocity field, and that three-dimensional picture of the plasma velocity field runs along these little tubes of plasma. I hate to use the word tube, but all I mean by that is some arbitrary, you just draw a line, any arbitrary line you want across some magnetic fields, and you extend it in space. Then the velocities along this thing are well known from observations due to the spectroscopy with the lines, Doppler effect, but also on the plane of the sky, you can also measure it. And that's pretty much all the information we know about the magnetic field in the corona from observations. That's until people, you know, work on radio in the 70s and 80s and look at very strong fields and active regions. And then just yesterday, the day before, you know, this paper with Deakis with the Stokes-V profile in the infrared. Okay, so what I'm talking about here is then a general problem in which we're mostly interested in transitions between these sharp levels because they give us this information and the continua don't. I mean, it's very hard to derive much from white light corona observations of the sun in terms of things like magnetism, because the electrons basically, all they're doing is they're impinged with a photon, they oscillate as a result of that impinging with a classical electric field, and then you can think classically, the electron is now going to oscillate in this direction, it's forced by the electric field, it's going to radiate, and we're going to see part of that. And so you measure polarization of that thing because, you know, you've got an asymmetry in the excitation, but you really don't have much idea from that. You can measure the mass of the entire corona through it if you assume it's fully ionized because the brightness is proportional to the electron density along the line of sight, etc., etc., etc. But the real stuff we're actually interested in, and if you look at the talks we had on, say, Tuesday, you know, almost everything is dealing with, not with continua, but with line transitions. So my obsession with, you know, changes in the internal structure is actually justified in terms of That's the most useful data we can get. And then if I embed an atom like this is just some random atom, I don't even know what it is, that I picked off the web. But you can see we have a richness in spectra from transitions between these quantum levels within these atoms that still have electrons attached to them. And so when we try to interpret the light from this thing, we basically do it in an optically thin condition. It's as simple as these three equations. What is the probability of making a transition from, say, this one to that one? Well, it's collisions by the plasma. This is local conditions in the plasma. And then we have a rate at which photons can interact. They can come from all over the plasma, deep in the, well, not deep in the sun, but from the sun's surface all the way out into the corona, say. And so we need to take into account how fast the transitions are between here. And then we want to solve a set of equations given these things for what the number density is in these things. Now, this is the deterministic equation, right? But we know quantum mechanics is not deterministic. So what's going on here? Well, this number I'm talking about is the number density per unit volume of an atom in a state I. Like, what is the number density of hydrogen, n equals 2 level? Well, it's the sum of all the levels that aren't n equals 2 of transitions from those levels into the level that we're interested in. But then, because we have to have, once it gets into that level, just like a level in level J decays to a level I, and should produce a positive term here, level I itself is going to have terms that remove numbers from there. So, and notice that we've got a dd by dt here, right? Now, this equation is just a heuristic equation. It comes from a master equation with quantum mechanics, in which you just say, well, you know, what is the rate of at which the levels go from here in terms of quantum physics? This P is deterministic. This C, for a given temperature and density, I set it and I calculate it, and it's an analytic formula. This thing depends on the radiation fields. They're all analytic. There's a J, it's well determined. So what these things are is just very simple. It's just their averages. For instance, if I have a level here and I say the Einstein A coefficient is 10 to the 8 per second, that doesn't mean that every atom in that state drops at exactly 10 to the 8 per second. It means that there's a distribution of, if I plot the number density of time, I have an exponential curve of e to the minus t times 10 to the 8. And so after 10 to the minus 8 seconds, I've got e to the minus 1 probability of finding an atom in that state. 10 to the 8 seconds, like e to the minus 2. And so what it is this is just saying that, you know, this is a deterministic calculation, but it's valuable because we have such a vast number of particles in these plasmas that on average, you know, this is going to be a rather accurate description for the average number density. And if we look at the number densities we get, if we have like 10 to the 11 particles per cubic centimeter in the low chromosphere or in the mid chromosphere of the sun, and I'm observing a megameter cube size volume, that's an enormous number of particles, the square root of which is tiny. So I can use a sort of, so this is a mix between a sort of classical idea. A classical idea would define this has to drop once every 10 to the 8 seconds, right? Quantum idea says no, there's got a probability of dropping which goes e to the minus t divided by 10 to the minus 8. But it amounts to the same mathematics, and that's what we're doing. And at the bottom of this thing, if we have a once we have some kind of solution here, if we think we know what the time dependence is, now this is Matthias's sort of area, right? What the hell is actually going on in a set of equations for mass, momentum, energy to determine something like this rate of change of these things in the plasma in the sun? But if we have some kind of model, and you know, I can ask Matthias to say, please, can you provide me with a number of with an expression for the density, temperature, and velocities of the particles of, say, hydrogen type. Can you just give me those out of some calculation, and I will compute this set of things here, and I'm going to end up with a time scale here, right? I'm going to end up, he's saying, you know, we've got 10 to the 12 particles that are 10 to the 4 Kelvin, and they're moving at 20 kilometers a second, and we have a v dot grad term in here, and we know we could compute what this, what the left-hand side of this equation should be. No, we're given x as a function of t, so we know what this is here. And so we then put this on the left, and we'd say, well, let's find out what the population is as a function of position and time. And there are certain limits. So for instance, if this is a very fast process, like 10 to the minus 8 seconds, it drops down immediately. 10 to the minus seconds, it's gone. 10 to the minus 9, sorry, 10 to the minus 7 seconds is e to the minus 10 of the population that we had before. It's just disappeared. So what I can do is turn the idea around and say, well, maybe I don't know what the sun is doing, and maybe even a genius like Matthias can't model it well enough for us to really trust this stuff. So instead, what I can do is I can look at the nature of these terms here, because given n, t, and what have you, I can get an idea of what these are. And it turns out there are two kinds of levels. One is very low down, in which the largest term here is very small. It takes a long time for this thing to relax, no matter what's going on here. And then I have a kind of level up here, which is just falling down like rain pouring out of a cloud in a deluge. And so the time scale for that level here is very small. So what I'm going to end up with is a set of equations here. And this is what I want to talk about only for the rest of this, 20 minutes here. And this has been a long introduction, but is how this thing evolves in time, and what we might learn from just looking at this without reference to magnetohydrodynamics or plasma physics or anything like that. As you can tell, there are certain characteristic timescales here, right? Which, if you've got something going on determining the plasma properties on the left-hand side from a physical model, this thing is either going to be able to respond or it's not in time. And one specific example I want to give you is that the chromosphere responds too slowly for this thing to be if I just look at the right-hand side here, it responds too slowly. It takes about 100 seconds for this thing to settle down. If I put x in equilibrium, I set that to 0. Now I can solve that. I can solve it subject to the idea that the total number of particles has to be fixed. So to replace one of the rows of this, remember this is going to be a matrix here, this PJI, and the diagonal part of the matrix is going to be a sum here. Here is the vector. This is a vector product. This is a product of one component with the sum over the terms in the vector in the matrix. So I'll show that in a minute. So, but what I'm talking about here is basically that the chromosphere is a place where these things from these estimates in here are just not fast enough to reach an equilibrium. And this is in fact state of the art in what Boomerang is at right now, because just happened to be on Tuesday, Matthias and I were talking about the fact that, can we do a fudge with this? What can we do in order to take into account that the hydrogen atom doesn't have time to relax to a fully equilibrium state? And so when he puts in a fully equilibrium state, he's going to get the answer wrong, but he wants to correct that roughly. How do we do that? And I'm going to show you where that comes from. So when I was waiting for a second bone marrow transplant, this is probably the illest I've ever been in my life, is about this kind of date here. And there's nothing like being ill, sitting in a hospital, bored to death for months on end, to make you think about things, right? The other thing that I think is nice as well is that, and I was talking to the people at the Wednesday celebration of CMAX. Sorry you weren't there, Joe. or I didn't see you. Maybe you
I'm
got that
not
a
on
little bit.
Siemens. I started out on Siemens, but
Oh man, you should have
I
come.
wasn't.
The guys,
You
the
have to
guys.
select your co-eyes carefully. I don't have that level of expertise.
So they were, yeah. So anyway, let's move on because time's running on. So so I was so ill that I didn't have much to do, and I had this sort of thought that, you know, I must be able to do something better than what we're doing here. In 1997, I visited Mats Carlson, and he was trying to understand the evolution of this kind of equation, no matter what this was. He was just interested in a partial d by dt here and finding a way to understand how this system evolves. And it's a simple linear equation, right? I mean, it isn't linear when we have redshift transfer, but if we fix these rates here, we can just start an initial state, let it go, and see what happens. And one example of this is experimental technique developed in the early 20th century, beamfoil spectroscopy. What's that? Well, what we do is we rub a few atoms together here to get the charges off them. So we've got positively charged iron here. We put an electric field across this thing in the lab, and we put a foil here. And so this thing is ripped up here by, say, a KeV, right? So it's moving at some wicked speed. Hits this beam foil. What's a beam foil? It's just a thin, it hits a foil. It's just a thin aluminum foil. Like you put your turkey in it, you know, next month or the month after. What happens then is, all hell, as this thing is coming through, you know, Rutherford scattering, very rarely does the have a head-on collision between the incoming ion nucleus and the nucleus of the aluminum or whatever it is. That's almost never going to happen. I mean, it comes straight back at you, and you know, Rutherford said, "Christ, the atom's got to look like this and not like a current bun." You know, I mean, this amazing history. What happened there is, instead, what happens is the atoms carry a lot of mass, the ions. They got electrons around them attached with a few hundred EeV, a few tens, few hundred EeV. And if it happens to get in the region of one of these aluminum atoms, it rips all the shit out of these electrons. So suddenly you've got an iron plus atom, which you made by rubbing some stuff together or warming it up or something. You've accelerated the crap out of it, and then coming out of here. And if I look at the atom at this stage coming in, it's got one electron removed, but it's moving at 100, it's moving at a keV. Now it's coming out of this side, suddenly it finds itself moving somewhat less than 100 keV energy, but it's now got a state where I've rattled the shit out of this thing, and I've got a whole bunch of I've ripped one electron off, and so I've got, instead of an atom in this lowest state here with one charge on it, I've got all these other states all rattled up. Now I've got an initial state, and it's flying along in space. There's no electric fields that I've imposed on magnetic fields or anything. So it's exactly this problem. I start from an initial state, which is one of high excitation, and then it's going to evolve like this. And then they watch these things go, and you can see these exponential decays, and you can read off from these things what the lifetimes of the levels are. And this is called beamfoil spectroscopy. Okay.
So there's no significant event.
Yeah, there's nothing that you basically just, you know, shield your region.
Yeah.
And then you just watch the radiation coming out of these things sideways on, and you've got a bunch of these, and you can measure the decay of these things. And because you're moving fast, 10 to the minus 8 seconds translates into a long distance. So you have a little photomultiplier here, you have another one here, you have another one here, and you've got everything you want to know about this thing. Beautiful. I mean, so simple. Okay. So we have the rate of change of the population. So now we're starting from an initial state, and we've got a lot of excited levels here. So X in the excited levels is very large. X in the lower levels is very small. And we have sources and sinks, so of these, at this level I, this happens to be just for whatever lower level or whatever level you want. And actually, there was a really nice piece of work done by somebody at HAO, Stanowoki, in the late 70s. He actually looked at the outflow of the solar wind. And if you look at this and you expand this in terms of, this is a sort of Lagrangian picture, but if you move just to Eulerian, you have partial d by dt plus v dot grad there's a V dot grad of the population of oxygen ions and iron ions in the solar wind. These are things that are frequently measured and have been, okay? And so he's saying, well, I'm going to ignore the d by dt. I'm going to say we're in a steady state. So we've got steady solar wind flowing outwards. And I've got a source and sink of these populations of iron and oxygen atoms. And I'm going to try to understand how this evolves in time. So what he did was he made the following, made a postulation that there's, let's move on. This one. Okay, obvious thing to do. It's a linear system. We're going to find the eigenvalues of this thing. Okay. And he subtracted off an equilibrium solution, which is one that doesn't depend on time. And if I've got, what is an equilibrium solution? It's one with lambda equals 0. It's as simple as that. Okay. So he subtracted that one off and came up with a beautiful thesis on how, instead of solidity equilibrium with ions having a proper having a population dependent only on temperature. Remember the kernel approximation? We talked about it only depending on temperature. If this thing is outflowing, and what happens is by the time this atom, oxygen atom has got from here to there, it hasn't had time to recombine. And now it's gone because the density dropped so much, it's never going to recombine. Whereas if I put in the local temperatures here for recombination, I'd find a hell of a lot of oxygen atoms. So what's going on is that basically this part of the equation is non-zero, and Iwaki was finding a solution for the x's, giving us an initial state, and given the slow coefficients for ionization and recombination, and ended up with a beautiful model of the solar wind, of the abundance ratios of the solar wind, which is still valid today. I mean, the beauty of those things is they were captured by spacecraft at 1 AU and somewhat further in with Helios and other things. But also now, people have been doing this with UVCS and other things on SOHO in the 1990s, much later. And so the radiation captured from these ions, not only is the dynamics causing the X-eyes to change, but it's directly reflected in the spectra through these equations here. So we should finish up here. I've done a lot of reintroduction of what we were doing, and I haven't got as far as I would have liked. But let me just show you what we'll focus on next time. Okay, you know, why am I so obsessed with these rate coefficients, P, I, J? I mean, the problem is it's almost everything. If you talk to Robert Rutten, rest in peace, about rate of transfer, there's a link between these PIJs and the rate of transfer equation. Two separate sets of equations. You absolutely have no choice but to solve for these, what the state of the atoms is in these discrete bound internal degrees of freedom. And then you've also got to solve for it. When I reach the ionization potential, you've got ionization. If I have a photon with enough ion, you've got to solve for the state of the atoms. And that's true no matter what the hell you do. Even the most elementary stellar atmosphere work, you have to know the state of the hydrogen atoms. This is why Cecilia Payne-Koposhkin thesis is deemed to be the best one ever in the history of astronomy. It's because she came up with a result contrary to Russell, you know, this Hertzsprung-Russell and Russell-Saunders coupling at CU kind of guy. Authority. He was dead wrong. Worse than that, he got credit for it. He stopped her publishing her thesis, and then he published it himself when he realized that he was dead wrong. I mean, my God, I mean, he should have gone over to Germany and joined Hitler. I mean, that kind of attitude is just appalling. I mean, the guy's a great scientist, but man, talk about a lack of respect. I mean, honestly. She showed that everybody was thinking in 1928 that, like on the Earth, the most dominant elements on the sun were carbon, silicon, iron, you name it, what nitrogen, right? Everything we're based on. Maybe a little bit of hydrogen because we know that CHNOPS, CHNOPS, those are the life-giving elements. I mean, it's the first order. We need a lot more, obviously. But what's going on was she showed immediately that the equation of state of hydrogen is so utterly different from what the equation of state would be on the Earth: ionization, recombination, LTE, Saha equation. She said, no, this is deadly. You got 10 to the 4 times as much hydrogen, or 10 to the 3 as anything else. And he was like, no, these results are spurious. This is where it comes from. What am I plotting here? Let's just finish with this one. We have, what is this thing? This is Pij for calculation taken from a calculation done for the middle of the VAL chromosphere, or something like this. So it doesn't matter what dimensionality it is, the thermodynamics and everything, they determine the rate coefficients. And if Matthias did something like this and installed it in Moorham, he would end up with a sensible looking chromosphere, I think. So what's going on here? So we know, first of all, that we have rates going from this level to that one. So this is sorry, this is in reverse, or this is Python. So what this means is that if we have a large number, we have an enormous rate. This is a probability of making a transition. It's 10 to the 8 per second, 10 to the minus 2 per second here. So now this is a full matrix, and it goes all the way from here to here. Notice these. There's nothing in this row at all. Okay. What is this? This is, I haven't told you something critical here. These are bound levels of hydrogen, and this is the electron plus proton state. So this is just it's just got enough energy to jump over the edge, and now it's free. Notice how small that is. It's down at 10 to the minus 2. That's what I'm saying. It takes 100 seconds for any changes in these lower levels to be felt up in these levels here. It's exactly the result Carlson and Stein got in 97. I showed Max Carlson what his thesis was in 95 or something, and Max went, oh yeah. Then he published his paper with Bob Stein on Radin, showing how the ionization, you have changes in thermodynamics, but the ionization doesn't change. That's exactly this result. It's this simple. Not one mention of a walkie, not one mention of me. All Carl's in that paper. I stopped working with him in 2000, I think. I was like, excuse my language, fuck that. I mean, that is just unethical. I mean, it's apart from poor, what's it called? Scholarship. I mean, you have to cite the literature on this stuff. Okay. What's going on here is that these are very fast. So we have 10 to the 8 to 10 to the 4. So in this region here, this is stuff decaying down very quickly, and this is decaying up. What I'm talking about here, this is stuff coming down, and again, that fit when I last looked at it. So we've got stuff going up. So we've got collisions and radiation going up, and we've got radiation and collisions coming down. We've got things called metastable levels. What do I mean by that? I mean, the diagonal part is the total rate out of this thing. It's the sum over each column, and I changed the sign of it. It has to be a minus sign reality, but for plotting, I've changed the sign. So this level and this level, these are really slow. The rest of them go like hell. So we've got separation of timescales in the atom. What this basically means is the whole atom falls down to the ground state in a very fast timescale, owing to these matrices elements here, or it's got, or it's in the atomic proton plus electron state, and it takes for ages for a proton to meet another electron and then come down into the bound states again. So you've got a separation of timescales here, and this will be used. And that now, if I look at multi-level atom, multi-stage atom. Okay, remember we talked about a variety of things. So So we have a carbon atom with one electron removed. That looks like boron, right? And it's got its levels in it. Now we take another electron off, and that looks like lithium. So that's got a 1s squared, 2s electron on it. Now, and so this is all part of, it doesn't know it about us calling it an ion. It just knows it's got these levels, of which we expect there to be some metastable ones from hydrogen. This is a 1 electron atom. This is a, and so now we go to carbon 2 plus, carbon 2 plus, carbon 3 plus, carbon 4 plus. And we just look at this rate matrix for those things. And we see we've got zeros everywhere. So whenever we have a little square, that's just the rates between carbon 2 levels. In fact, I should have all these levels, all these should be non-zero, because we can certainly take a beam foil, right? And I can slam a carbon plus atom going at 1 keV, and then afterward it comes out in a carbon 4 plus state. So that would give me a matrix element here, right? So I generate carbon 4 plus from carbon plus. But in plasmas, that's not the default way in which things generally happen, unless you're really far out of LTE, like in equilibrium, like a very rapid flare, right? So what's going on is that we can treat these things as separate ions. I mean, this is almost block diagonal, right? That means that these levels are completely separate from these ones. They're completely separate from this one. And remember, we've got this carbon 4 plus level here. That's hydrogen, helium, right? So that's got 2 electrons around it. 2 electrons, opposite spin. That's very deep down in the potential of a carbon nucleus, right? I mean, it's really stuck down there. So it ain't doing. Again, we've got, look at this. We've got quite a few metastable levels here. These are down in this region here, 10 to the 2 seconds. Now we've got a really big one. Oh, that's 10 to the 8. What is that? I've included a level that's a resonance line of carbon above carbon 2. So it goes at 10 to the 8, drops. That's what we observe with Iris, is this one. It goes from level 3 to level 1, according to where it is on this matrix thing. So it's 3 up, 3 along and 1 down. And then, so that thing is going to decay like crazy down to here. Now, if I diagonalize this matrix, which we'll get to next week, I would be able to tell you what the eigenvalues are from just looking at the diagonal elements. That's standard. And that tells me from my expansion, where is it? Yeah. That tells me that I know each one of these, and I know how to understand the evolution of this thing in time. But I want you to draw your attention again to the idea and leave you with this idea. That is that here we have all these, anytime we have one of these above the diagonal, we always have a diagonal number, and that's just the way the mathematics works out. It's just, that's the sum over the column. This element here is the sum over the columns, right? So here we've got all the levels that are going to disappear out of our equation of motion, equations very quickly, but they're also the ones that are going to be brightest in the lines. Okay? So these slow processes here are going to determine how this thing tries to reach an equilibrium. In the meantime, it's going to carry along with these quick decays, these very, very bright levels, which are related to the brightness, because the bigger the probability, transition probability, the brighter the line is, generally speaking. And so we have a nice situation. And what I'm going to do next time is talk about a couple of things. More details about these matrices, to nice analytic work which can be done. And this is all from this, and this will be familiar to those of you from undergraduate math maybe or something. And then we're going to look at a couple of really nice tutorial examples in which I derive analytically the eigenfunctions of this thing. And then we're going to look at how they evolve in time. And then we're going to look at something, take a step back, about 60 years to a time and place where computer calculations were expensive. And people came up with some simple ideas based upon the separation of timescales like I'm talking about, in which you end up with a way to understand a recombining plasma. What happens if you have almost everything in the ionized state and a little bit of recombination down to the neutral, ion 1 versus ion 2. And if you have an ionizing plasma, and these people, there are some people who talk about ionizing plasmas, time dependence, in terms of something called the collisional radiative model, which is an approximation which is used to understand and diagnose non-equilibrium effects in flares. All right, guys, sorry I went over, but I so enjoy talking about more general things like the origin of the universe and how we understand things.
Maurice has a question.
Yeah, Maurice.
Sorry.
If your question is, can you go to the bathroom, then the answer is yes.
Sorry for interrupting the recording. You can finish your outro if you need to. I don't know how this recording thing works.
I can push the stop button now.
Yeah, that's fine.